Stuart now.
Okay, so hi everybody, I'm Stuart Golodetz. I'm here to talk about our kind of work we've been doing on kind of large-scale collaborative reconstruction. So this is joint work with these guys down the bottom here. Okay, so basically what we're trying to tackle is kind of reconstructing sort of like dense 3D models of things like a whole building, sort of like at a much kind of large scale than kind of people would tend to have done with things like kind of, you know, sort of kinetic fusion systems. So if you ever kind of wandered around with sort of like that kind of system, you'll find that sort of reconstructing beyond a certain scale kind of gets a bit frustrating. So people tend to kind of wander around sort of in front of your camera, and then you have to do some reconstruction, or your tracking tends to drift, or it's just taking you a really long time, sort of like doing it from your own. Okay, so basically what we're trying to do is have multiple people kind of wandering around, constructing sort of like different parts of the scene. So this kind of reduces the amount of time it takes. If it's like individual bits of the scene, great, because like someone walks around in front of the camera of one of the agents, you can kind of just recapture that bit. And we use kind of visual inertial odometry within each of the agents to kind of help use the tracking drift at a particular scale they're capturing at. And then when we join the kind of bits together, you get a sort of like more globally consistent scene. Okay. So just looking at kind of some existing works, they kind of fall on a spectrum. So they're kind of sort of low-cost, sort of like interactive methods, like so the sort of things kind of built on top of sort of like kinetic fusion. So for example, this is an adapted version of sort of Matthias' niceness, sort of like voxel hashing thing. It's like a sort of particular sort of implementation that with some improvements in certain areas. So Olaf Kahler, sort of like back in 2016, this work where basically you split the map into like segments as you're going around, and then kind of when you close loops, you kind of adjust them relative to each other with closed graph optimization to like make a consistent map. There's also things like bundle fusion, where sort of you bundle adjust these sort of like individual frames and sort of then kind of reintegrate them at their sort of new poses. Both of these things kind of produce quite nice maps at sort of this kind of scale, sort of scale case, like green scale, sort of like, you know, sort of a part of the bookstore. But if you kind of try and scale them up to like, you know, sort of to sort of like hundreds of square meters, then they tend not to work so well. At the other end of the scale, you kind of have like much higher costs for like offline methods. So these things can do kind of large scale. So if you can have like a map port scanner, you kind of go around to like places at lots of different locations in the building. Each of sort of like the individual sort of like map segments takes 1 or 2 minutes to sort of, you know, for all the setup and the kind of reconstruct. Then you kind of join them together to sort of like make a nice map, but it takes you quite a long time. Similarly, you can go around with something like a sort of like Barrow 3D, which is like a sort of laser rangefinder. Again, kind of, you know, make sort of like chunks of map and join them up, so like up and up and back. But again, it's like taking one of these scans and physically putting it in lots of different locations is a bit of faff, and so like this, so this whole process can kind of take many hours to actually kind of get the high quality results that you kind of see here. Okay, so we're kind of aiming at sort of like, you know, sort of large scale, but in a kind of much shorter period of time, with a kind of a focus on kind of like, you know, getting a capture sort of quickly with lots of different agents. So basically, sort of like what we do is, so you see all of the kind of different kind of individually coloured map segments here were sort of reconstructed by one agent, and sort of like then we can join them either after the fact or sort of like while the people are wandering around to make the combined map. So yeah, I mean these are showing the optimized poses, but like in the sort of well, when you're actually doing the problem, then you don't have a transformation between the individual segments. This is after they've kind of been aligned, just to kind of show you how they fit together to make the overall scene. Okay, so to show you kind of the architecture of our system. So basically what we have several clients and a mapping server. So each of the clients like feeds posed RGB frames to the server, which kind of reconstructs a subscene for each client and trains a local, so like a 6D pose, like a camera relocalizer for each of the individual subscenes. And so basically the idea is we want to find the relative transformations between the subscenes of different agents to join them up to make the overall map. And we want to do this kind of while the agents are still wandering around, so we do this in the background while it's happening. So basically, so last year we did some work on camera camera relocalization and so we've got a kind of high quality camera relocalizer which can relocalize from novel poses. Basically, you give it some pictures of the scene and it kind of estimates where the camera that took those pictures was in the scene. So in the context of this thing here, what we do is if you wanted, say you wanted to find the relative pose between the subscene of one agent and the subscene of another agent, you imagine taking a picture from the camera of one agent, passing it to the local relocalizer of the other one, and it will tell you where that particular image is in the frame of reference of this agent. And using that, you can then get the relative transformation, well, a sample of the relative transformation between two scenes. If it's accurate, then you only need one, but we'll talk a bit more about that later. Okay. So basically, the issue is which image from a particular scene do you feed to the other one. One thing you could do is, as you're going around with the individual agents, you're kind of capturing a sequence of images for each agent. You could store those and then kind of pick one later and relocalize it against the other scene. In practice, that would take huge amounts of memory and doesn't scale very well. So what we actually do is we instead store the trajectories for different agents, and because we're reconstructing 3D models of the individual subscenes, we then render, later on we kind of pick a pose from the trajectory of a particular agent. We render the model of its particular scene from that pose, and we take a synthetic image and we pass that to relocalize with the other scene. So then, as I said, if the relocalizer then kind of returns a pose in the other frame of reference, you can use that to get relative transformation between the two scenes. And yeah, so in particular, that gives you one sample of the relative transform between those two subscenes. What we actually do to get a bit more robustness, because sometimes you can get a pose which may not be right, but it's there's a certain percentage error there. We try and get several samples by relocalizing several different images with that relocalizer and cluster them to try and pick one which we're fairly confident about. And based on that, I'll discuss the individual bits in a bit more detail in a second. But then we take the biggest cluster of samples between each of the different pairs of subscenes, use them to kind of make a pose graph and run a pose graph optimizer to move the individual subscenes around a little bit with respect to each other to make sure that you've got consistent relative transforms between subscenes, and then we render them wherever they've kind of been placed using the global scene renderer. Okay. So the inter-agent relocalization step, this was the kind of thing I was just describing, so in a little bit more detail. So you've got a particular frame pose in B, and you've got this. So say this is, you're trying to relocalize the scene of an agent B against the scene of an agent A. You've got a particular model you've been running to pose. You render that scene at that particular pose. You pass those to relocalize to the other scene. And this will either give you a pose in the frame of the other scene, or will fail. If it succeeds, then you try and verify it to check that it's correct. And so basically you render the other scene from the pose you've got. If that will kind of give you a depth image of the other scene that you kind of compare the two. And if they're similar enough, then you say it's verified, and you take the relative pose which you've therefore figured out between the two scenes and add that as a sample of the relative transformation between the two. Okay, so you build up basically. So it's essentially what's going on as you're kind of going along. You repeatedly kind of pick two scenes that you want to try and localize against each other. You and do this process, and you accumulate samples of the relative transformation between the scenes. So for each pair of scenes, you build up the clusters of these transforms like we're seeing here. And we say that after you've got a certain number of consistent samples between each scene, you get relatively confident about the transform between them. So basically, whenever we add a new sample, we look to see whether we now have a confident relative transform between the two subscenes in question. If we do, we then run a post-graph optimization process based on this. Okay. So essentially, you have nodes for each of the subscenes and edges, which are I think with the confident about the transform between subscenes, the one you likely believe is most likely. And so you basically, what you do, you take the samples in the biggest cluster for the in between each pair of subscenes, the ones you're confident about, and you kind of blend those poses using dual Quaternion blending. And you make a pose graph, and then you run a pose graph optimization process to, like I said, move the subscenes around to make the overall system that. Okay, well, I'll tell you what it's supposed to say. Basically, what you actually have there is you've got a set of terms. So for each of the edges, you've kind of got an individual error term. And basically, the idea is you've got the relative transform, which you've been estimating between scenes, and you've kind of got the global poses at either end, and you're trying to make the two, well, sort of like the relative transformation implied by the two global poses match the relative transform you've estimated between the two, and you alter the global poses until that's the case. Yeah, this was made on a Windows machine. This is not a Windows machine. Okay, so that's this. So importantly, we kind of do all of this pose graph optimization and everything in the background. So as we're wandering around, the things are being kind of moved around with respect to each other, just like live as you're sort of wandering around. If you do all this, here are some examples of sort of maps we can get out of stuff. So basically, you can try this in several different scenarios. So, for example, you've got like a 2-bedroom flat. There's like a 3-story house there. There's a lamp down the bottom left, and there's like it's like a 2-story house, 2-story 4-bedroom house there. So, for example, like these are some of the sort of bedrooms, that's the stairs, and so on. Okay, so several things to remark here. One of which is because we're using visual inertial odometry within the individual subscenes, they're kind of locally quite consistent. So you'll notice that the walls are quite straight. Separately, you'll notice that sort of because the relocalization between subscenes is working really well in the pose graph optimization, you don't kind of see obvious seams in most cases between the different subscenes. Okay, so in terms of how good the reconstructions are in practice, so basically we evaluated this. We had a laser rangefinder. We didn't have a LiDAR available, so we kind of ran through reconstruction as part of it. But we had a laser rangefinder, and we measured. We took certain measurements on both in the real world with the laser rangefinder, and we also combined mesh models of all of the different subscenes together, posed in the right place in MeshLab, and did the same measurements in MeshLab. And just like to give you a few examples of like how we selected the laser rangefinder. So as far as I remember, so the first number here is the rangefinder, and the second number here is the number of the mesh. So you can see they're kind of within a sort of few centimeters in each case. So you're getting fairly consistent reconstructions out of that. Okay. From a time perspective, so we got several mobile devices, wandered around, reconstructed the office, and so basically you can see, even with a number of clients connected, what happens is you've got several different things going on. You've got this kind of right along the bottom is the kind of fusion of subscenes happening on the server. So I mean we're building on a kind of very efficient fusion engine, so obviously the cost of that is pretty low. That's all kind of very real time. These lines here, you kind of see this is the time taken to kind of do the integration relocalizations and pose graph optimization. So because of the way we're doing that, where you're kind of doing them sort of one at a time and gradually accumulating samples between the scenes, again the cost of that's fairly low. So in practice, this whole thing runs kind of very interactively, and you can kind of just wander around spinning things across the server, optimize everything in the background, and it's nice real time. So in terms of how long does it take to actually kind of make these kind of different models? So basically, this is the number of these were kind of done in practice by me wandering around, kind of reconstructing lots of separate ones and doing them after the fact. But if you imagine some people wandering around In parallel, if you actually had enough devices to have 6 devices as you walk around, this is the amount of time it would take so this is based on kind of the longest sequence of the ones you do when you join them up. That's how long that would take to do. And so if you've got other people wandering around at the same time, you're doing that in parallel, so that the cost in practice is dominated by whoever takes the longest. And the average collaboration time is, if you, this is kind of joining them after the fact. So that's the average time it takes. If you try this like 5 times, and you see how long it takes to kind of join them up, that's roughly how long it takes on average to kind of join up those sequences after the fact, right? So this is the time taken to kind of join those 6 sequences into one. So depending on the difficulty of the relocalization problem you've got there, it takes more or less time. So in the case of the flat, it's a fairly small scale, there's a decent amount of overlap, it's fairly quick. In the case of the lab, we were kind of doing individual floors of the lab. There's only a certain amount of overlap. So it kind of took longer because you'd have to test more frames to find the ones which work, basically. But in all cases, you can see, that's sort of under 20 minutes in each case. So for something like the size of the lab, so that this was sort of, we kind of worked out from the floor plan, it was about 820 square meters. So things like of a similar size, if you kind of wanted to do that with like a sort of Matterport scanner or something, it would take a lot longer than that. So that in practice is quite fast. So in terms of the memory usage, basically we took the kind of 6 sequences which made up this kind of 3-story house, and we kind of worked out what's kind of like the sort of minimum memory usage you can have when you're doing that. So basically kind of the sub-scenes kind of one at a time, like fed them through the pipeline, relocalized them against each other, and after sort of like finishing the training for each relocalizer, we dump the training data. So this is why you kind of see the lines dropping there. So it's essentially the headline figure is it's kind of like roughly a gigabyte of subscene, so on like something like Type Next. But with driver overhead included, you end up being able to do up to about 11 subscenes on one of those. The relocalizer, after you've done the training data, is about 500 megabytes of relocalizer, so you can have rather more of those. But the limiting factor is basically the memory for input subscenes at the moment. So I've got a couple of videos to show you. How much is it? I'm not sure actually. So here's an offline. No, sorry, 1 second. Have this. Slightly silly user. You are not getting rid of your game. Sorry, content mirroring on.
People move around, your battery or memory runs down, your traffic fails, or your capturing device never repeats. We circumvent this problem by allowing sequence captured interactively in multiple pieces and stitched together. In this video, we show how this works by reconstructing a 3-story house from 6 separate pieces. Initially, one or more users reconstruct 6 overlapping parts of the house using consumer-grade augmented reality smartphones, so using small images surrounding the window. The images from each smartphone are transferred to the server and reconstructed alongside each other to make a subscene 2, the main window.
These are depth sensing cameras, or
it says 87 frames, so it's got a 5 Hz depth camera. Yeah.
Once all of the house parts have been reconstructed, our inter-agent relocalization and post-bump optimization process stitches them together to form the final house. With multiple users reconstructing the different parts of the house in parallel, this process allows us to reconstruct a globally consistent model of the entire house in under half an hour.
I'll just pause that and show you the unlock, because I think that's doing quite okay. So the other,
In this second video, we show two users interactively collaborating to reconstruct part of a research lab. As the users move around in space, their clients feed images over Wi-Fi to central server, which reconstructs a subscene and trains a local relocalizer for each client. Periodically, the server attempts to relocalize one subscene against the other. Initially, the two users explore different parts of the space, and a confident relocalization between the two subscenes cannot be established. Eventually, the second user visits part of the space that has already been visited by the first user. At this point, the server can determine relative transport between the two subscenes and establish a common global frame. Once this has been done, both users can continue to contribute to the map, allowing the scene to be reconstructed more quickly than with one user alone.
Yeah, I think that's been done mostly. Does anyone have any questions?